Review session for exam number 1 in ME143 fluid mechanics. Let's start with a couple of definitions and the mass flux and mass flow rate, which there you go, for which we defined a surface S with a normal to the surface N and a flow flowing through that surface at a velocity V, and the velocity vector makes an angle theta with the normal vector. So both, as you can notice, both the mass flux and the flow rate depends on the scalar product between V and the normal to the vector. And just as a reminder, it's a very important reminder, this is the mathematical definition of the scalar product, and theta, cosine theta is equal to 1 if theta is equal to 0, and to minus 1 is if theta is equal to 180 degrees. Second important definition is the Reynolds transport theorem. Again, we consider a control volume CV. Here we're going to assume that this control volume is fixed, and we have a flow passing through that control volume. Important too, don't forget to define the normal, the local normal of your control volume. And the Reynolds transport theorem states that for any property B and its associated intensive value beta, which is defined here, the variation of B within the control volume is the sum of the temporal variation of rho beta within the control volume plus the flux of rho beta across the surface area across CS. This is CS, that's the surface that bounds the control volume. Now, in the unique case that you have a control volume of variable surface, I'm sorry about that, let's backtrack quickly, it was the wrong button. So in the odd case that you have a control volume that, say, expands, so you have CV at T, and now you are expanding this, and you have CV at T plus delta T. So in this particular case, which again is not that common, and I can tell you you will not be asked to solve this type of thing at the exam, here we can define Vs as the velocity of the surface, and now we have a relative velocity, Vr, which is the velocity of the fluid, because we still have a fluid flowing through this control volume, minus Vs. And the modification to the Reynolds transport theorem comes into Vr, really. So that's the only modification. So again, in the exam, this equation will not be useful, but it was just for your information. So, how do we apply the Reynolds transport theorem? First, we look at the conservation of mass, and again, we consider a control volume, CV, with a local normal N, so that's your CV, and we have fluid flowing in and out of the control volume, And the conservation of mass states that the mass of the time variation, or the variation of mass within the control volume, plus the transport of mass across the surface area of the control volume has to be equal to 0. In most of the cases, the flow is steady, so that means that this first term disappears, and so you are left with really just the flux term. In most of the problem, you are asked to solve for the force of the fluid on something. Could be drag, could be force of the force against a gate, could be many things. So for this, you need Newton's law. But Newton's law in fluid has this form. That's the conservation of momentum. So again, this here is nothing more than MA is equal to sum of the forces. It was a very poor force. So you have your control volume, the normal to the surface of your control volume, so that's CV, that's CS, and then you have your flow coming in. Your flow is going to transport momentum through this term, and you have a bunch of forces that apply within the control volume. Could be also the weight of the fluid. You could have the force of pressure. You could have force of viscous forces or force of friction. Anyway, that's you need to list all those forces. Now the key, as we will repeat later, is to list all the forces that are acting on the fluid. So let's quickly go through the steps required to apply the conservation of momentum. And the first step is the definition of the control volume. So that's CV, and bounded by the surface CS. So the definition of the control volume. How do I define the control volume? Well, the best way to define your control volume is to consider, first of all, the velocity of the fluid. The velocity of the fluid is going to be given to you by the statement of the problem or by the previous question. And you want to define a control volume such that the flow on the surfaces is known on every surface. So again, don't forget, it's important to not only sketch the normal to the surface, but also label your surface so that you will have a good idea of what you're doing. So N1, N2, N3, N4. So let's say that the velocity is defined on surface 1 and surface 2. I want to choose surface 4 and 3 such that, for instance, V3 is equal to 0. That will vastly simplify my life when I have to calculate the integral over CS3 of rho V Vn dA. Similarly, I could have, say, V4 perpendicular to N4. and that will have the same result. There will be no flux on this surface. So the other aspect too is that it needs to include all the forces that matter, especially the one you're looking for, right? So that's pretty much key to define your control volume. Once you have defined your control volume, and one piece that I forgot, I'm absolutely sorry about that, is that you need to also define a frame of reference. So that has nothing to do with step 2, define assumption. You need to define a frame of reference. Now, for those of you who are a little shaky on vector calculus, I strongly encourage you to write down that N1 in the previous slide was minus I, N2 is equal to plus I. That will vastly reduce the risk of making error when you have to calculate this term, right? Because then you can just replace, say, in the previous slide we had the system like this, where we had N1, so let's say that I is going this way, and we have V1. So this term here becomes V1 times V1 dot N1, which is equal to the norm of V1 I times the norm of V1 I scalar product minus I. Okay, and so here that's minus 1, so this is equal to minus V1 I. Okay, so that's really important that you that you do define clearly all of your vectors. Now, define your assumption. Well, the usual suspect is the flow steady. Is the flow viscous or inviscid? Viscous, so steady, viscous. Does the hydrostatic pressure matter? Meaning that if you're dealing with water, do we have a height of water that is big enough that we need to consider the linear variation of pressure with depth? Does the weight of fluid in CV matter? I hope you can read. I can barely read myself, I'm sorry about that. So this viscous forces, hydrostatic pressure, is the velocity uniform. I forgot that one. So steady, this one, as far as steady, that takes care of this problem. And if the flow is steady, then you get rid of this. Does viscosity play a role, hydrostatic pressure, weight of fluid, all of this will help you find some of the forces. If the velocity is uniform, this one helps you compute the flux term. Step 3, define the forces. We just talked about that. The key here, the best advice I can give you, is that you need to answer the question, what are the forces acting on fluid in CV. Well, wait. What are the forces acting on the fluid in the control volume? Acting on fluid in control volume. Okay? You will never go wrong if you ask yourself this question over and over again. You will find all the forces that you need. Step 3, solve. Here, carry, went too fast. The key element here really is to carry vectors as long as possible. Unless you are just looking for one component, in which case you can project this vector equation, because yes, remember, it's a vector equation, onto one particular direction. You need to carry this equation as a vector equation for as long as possible. That will vastly limit the risk of error on your part. Lastly, it works for hydrostatics too, because for hydrostatics, everything that we've said is valid. All you need to do is to get rid of this term, get rid of this term, and solve sum of the forces equals 0. So really, chapter 1 and 2, only chapter 2 matters. Well, I guess in chapter 1, what we've learned is that if we have a volume of fluid at P atmospheric, where the surface is at P atmospheric, and that's Z, that the pressure at Z is equal to P atmospheric plus rho GZ. And the other thing of importance that we've learned in chapter 1 is that the force of pressure so let's imagine that here we have the fluid here, and we have P atmospheric here and P atmospheric there. Then if we consider the gauge pressure, then the total force of pressure, if we have a height of fluid h, so Fp is equal to rho gh square over 2 times b, b being the width of our system, times I, if we define I this way. Okay? So with this, you should be pretty much all set for this exam. Good luck.